Thanks for coming. I'm interested in the evolution of multicellularity, which is something that's actually happened lots of times across the tree of life. So animals, plants, fungi, red, green, and brown algae, each one of those groups represents at least one independent origin of what we might call complex multicellularity, or multicellularity with cellular differentiation. But there have also been lots of other independent origins of what we might call simple multicellularity, or multicellularity without cellular differentiation. The main thing my lab is focused on right now is experimental evolution using this unicellular green alga, Chlamydomonas reinhardtii. We like Chlamydia for a couple of reasons. One is that it's a model organism, and that obviously comes with a lot of advantages. But one of the reasons that we like it in particular is that it happens to be a close unicellular relative of this group of multicellular green algae that includes volvox, or volvocine algae. And what that means for us is that we can compare what happens in our evolution experiments with what we think has happened historically in the evolution of multicellularity in volvocine algae. So we've previously shown that selection for an increased rate of settling out of liquid suspension can drive the evolution of simple multicellular structures in Chlamydomonas. But we don't think that's a very common selective pressure in nature, a pressure to sink to the bottom of something. So we wanted to test an idea that we think is more ecologically relevant, namely the idea that predation might have driven the evolution of multicellularity. And this is an old idea. Here, David Kirk is talking about it specifically in the context of the volvocine algae. And it's a simple idea. The idea is just that in the pond and lake ecosystems in which these algae evolved, there are a lot of filter-feeding predators that are really good at eating things up to about the size of a large eukaryotic cell. And if you can get a little bit bigger than that, if you can get beyond what Kirk calls the predation threshold, then suddenly there are just a lot fewer things that can eat you. And this obviously translates into a big viability advantage. So we set out to test this using a really simple experiment where we started with an outcross population of Chlamydomonas reinhardtii. CC numbers there, just strain designations. And we co-cultured 5 experimental populations with this filter-feeding predator, Paramecium. We also had 3 control populations that were cultured without the predator. And what we found after about a year of weekly transfers is that 2 of the 5 experimental populations had evolved simple multicellular structures that we didn't see in any of the other populations. These things are basically spherical, and they have very stereotyped numbers of cells. They're almost all either 4, 8, or 16 cells, and I'll talk a little bit later about why that might be. Strikingly, they look an awful lot like some of the smaller, undifferentiated multicellular volvocine algae, things like Panorrhina, Volvolina, and Yamagiciella. Lab tech Josh Warren did some very detailed observations of the life cycles of these evolved algae. In the interest of time, I'm only going to have time to talk about the extreme ends of the spectrum here. So I'm going to skip over the fact that there are some intermediate cases, but you can find that in the paper with the full description. Of course, there's some subjectivity in classifying things in categories like this, but I think this is a pretty fair representation of the evolved life cycles, at least in cartoon form. So the left-hand panel here is basically the wild-type Chlamydomonas life cycle. And this is what we observe in all of the isolates from the control populations, and some of the isolates from the experimental populations as well. And I want to spend a little bit of time on this, because Chlamydomonas doesn't do binary fission like you might expect from some unicellular organisms. Instead, they do something called palintomy, or multiple fission. And what that means is that they grow to many times their original size, and then they divide 2, 3, or maybe as many as 4 times in rapid succession with little or no cell growth between rounds of division to produce 4, 8, or 16 daughter cells that are briefly contained within the mother cell wall. Eventually, the mother cell wall breaks, and these things are released into the medium as free living unicells. One of the reasons I want to spend some time on this wild-type life cycle is that I want to make clear up front that even in this life cycle of what's almost universally described as a unicellular organism, there is a transient multicellular stage, the stage at which the cells are divided but not yet broken out of the mother cell wall. At the other end of the spectrum, we see some isolates have an obligately multicellular life cycle, where we actually don't see any free-living unicellular state at all. What we see instead is multicellular structures releasing multicellular properties. So Josh also quantified a couple of different aspects of these life cycles, one of which was the number of cells per propagule. Now the y-axis here is on a log base 2, so this is basically the number of rounds of cell division that it would take to produce a propagule of that size. So what we see is pretty much what we expect. The isolates from the control population, which are these K1 isolates, are releasing strictly unicellular propagules, log base 2 of 0. Some of the experimental isolates are also releasing unicellular propagules. Some are releasing a mixture of unicells and multicellular propagules, and some are releasing almost exclusively multicellular propagules with median cell numbers up to about 8, log base 2 of 83. I hope I got that in the right order. We also wanted to know how big these things get. So this is a funny measure. It's the median number of cells per cluster at the time point during development at which that measure is the largest. We did it this way because not all the isolates reach their largest size at the same time point during development. So this is our way of staging these things, but I want to be upfront about the fact that this is not really a measure of central tendency. What we're really interested in here is just how big do these things get. What we find is, again, the control isolates are strictly unicellular. We have some isolates that are mixtures of unicells and multicellular structures, and some that are almost exclusively multicellular, with median cell numbers up to about 8 cells. That's not a log base 2, that's 8 is 8 there, not 2 to the 8th. So I'm going to show just a couple of time-lapse movies. Just in the interest of time, I'm again going to focus on just the extremes of this spectrum. The first one I'm going to show is of one of the control isolates. And this is the wild type life cycle that I described earlier. As I mentioned before, we do see the appearance of these transient multicellular stage, but that doesn't stick around very long. This is basically a unicellular population. At the other end of the spectrum, one of our sort of most multicellular isolates, we see something very different. We see multicellular structures releasing multicellular propagules. I want to be clear here that what I'm not talking about is these gigantic clusters of hundreds and hundreds of cells. We don't really think those things are meaningful. They're not held together by anything. If you vortex this culture, they'll break up. They're just forming because these things don't swim, so they tend to stay where they're born unless they get pushed aside by further growth. What we're really talking about here is these mostly 4, 8, and 16 cell clusters releasing 4, 8, and 16 cell propagules. And the way these things reproduce is actually really similar to the smaller Volvocene algae, the smaller multicellular Volvocene algae. It's a process called autoconvolution. And what that means is that each cell in a colony or in a cluster produces a single daughter colony or daughter cluster. And you can kind of see that in this cluster of 4 cell clusters in the bottom left-hand corner here. So this was a 4-cell cluster. Each of the cells within that cluster has divided twice through this process of palantomy to produce a 4-cell daughter cluster that's held, where the 4 cells are held together by the parental cell wall. The whole thing is actually still held together by what's now the grandparental cell wall, which will eventually break and release these 4 4-cell clusters into the medium. This is supposed to be a genomics of experimental evolution session, so I apologize for not having very much genomics to show. What I do have to show is all the work of my current postdoc, Kimberly Chen. And one of the things that she's found through whole genome sequencing is that the multicellular isolates from the 2 different populations are quite genetically distinct from each other. They show distinct patterns of recombination of the 2 parental genomes. So this confirms that they, first of all, had to be descended from different products of meiosis in the starting population, and second, that they are truly 2 independent origins of multicellularity in these 2 separate populations. One of the things she's doing right now is trying to get at what loci might actually be causing the multicellular phenotype, and one of the approaches she's taken to that is trying to introgress the causative loci into wild-type backgrounds. She's actually doing this reciprocally with both parental strains, crossing into the multicellular ones, keeping the multicellular offspring, back crossing them again and again, 5 or 6 rounds of that, with the hope at the end that what we'll have is some strains that are almost entirely wild type in their genome, but also multicellular. And so obviously they'll have to have whatever locus or loci are causing the multicellular phenotype. So we take several implications from this work. The first is just that it can happen, that the transition to at least a very simple multicellular life cycle can happen quickly. We've seen it happen in other experiments with Chlamydomonas by us and by other groups. We've seen it in all these other experiments I'm going to talk about, or other people's experiments. It's happened in an experiment with another green alga, chlorella, and it happens pretty regularly in experiments with Saccharomyces yeast. And in all these cases, we see the evolution of these simple multicellular structures within hundreds of generations. Second, we think this demonstrates pretty clearly that predation is at least a viable hypothesis for the evolution of multicellularity. Third, we see that these evolved multicellular life cycles have what is a key feature of almost all multicellular life cycles, namely the presence of a unicellular bottleneck during development. And this is often thought to function in preventing genetic conflicts among cells by maintaining genetic homogeneity among cells. And finally, as simple as they are, these evolved multicellular structures are at least potentially units of adaptation. The reason I say that relates to this unicellular bottleneck, because if you imagine a population of these things in a pond or a lake somewhere, it's likely that nearly all the genetic variation will be distributed among clusters within the population, not among cells within the clusters. And this raises the possibility that they can respond to selection through cluster-level adaptations. So I want to quickly thank some of my collaborators on this work, along with funding from several different NASA sources, including a postdoctoral fellowship, the Templeton Foundation, and the National Science Foundation. And I'll be happy to take any questions.
You mentioned that back-crossing strategy. Has that begun? And if so, do you have a sense of how complex this trait is?
It has begun. I think she's on her third round in one parent and fourth round in the other parent. That hasn't told us anything about the structure yet, but she also has done some, which I left out in the interest of time. In retrospect, I could have included it. She's also done some tetrad dissections that suggest that it, at least in one of the evolved lines, it may be a single focus.
Cool.
Can you still induce sexual reproduction in multicellular Chlamydomonas?
Yes, we can still, sorry, I should be repeating the questions here. The question is, can we still induce sexual reproduction? And the answer is yes, we can still induce sexual reproduction in multicellular strains. Yeah.
So you had 3 replicate populations that did not evolve multicellularity in response to predation.
That's right.
Do they adapt to predation at all as a first hunter?
We never tested that. We didn't, we did with these guys actually test that they survive better in the presence of predators, but we never did it with the other